this module 1, that is electrostatics. Is one of the first of its kind in this electromagnetic field theory and transference. So this is the very first starting, and I think you have all studied about Coulomb's law and the force, the electric force and the electric field intensity in the lower sessions, lower classes. But I'm not sure how far you people have understood this concept. But you will really understand the Coulomb's law and so-called the electric field all the way when you really apply upon any particular application. Let's say inside the semiconductor device, how the field distribution, all this is. We can even calculate them using the using all these principles which are used in the electromagnetic field theory. So it will be very exciting to understand. And you people can easily understand almost any electronic circuits if you apply these fundamental laws of electromagnetic field theory. So we will start with Coulomb's law, and we will keep on go other important laws very quickly. Well, I think all of you know about the difference between this static theory and dynamic theory. And we will start with the electrostatics, which is nothing but the static electricity, which means the charge or any other charged bodies, actually, they don't move. They will be static, and or they will be in rest position. So, and based on that, whatever the phenomena, particularly the force due to the charged bodies or the field intensity due to the charged bodies, uh, which are uh, which are rest uh, or which are static, and they will be understood through the course of the electrostatics. So I believe all of you know about these fundamentals of the electric charges. Uh, Mostly we can easily see from the subatomic particles like electron, proton, all the way. Also, this nature is available in atomic level. Like if you pick up a neutral atom and you take one electron outside, then immediately you will get the charged body. That is nothing but ion will come. So they will be positively charged or negatively charged. They are the easiest way one can get it. In molecular level, all of you know about that. Between two, let's say, sodium chloride, the sodium ion and the chlorine ions, they don't have one type of charge between each other. So by come together, they'll be sharing common electrons, and two electrons they will be sharing. Both electrons will be opposites. By the way, their binding will be much, which makes that particular crystal stable. And that is one of the very interesting material that which is even used for many electrolytes and all the way. So, that is where the so-called the charged bodies are coming into the picture, and sometimes this charged bodies may move, which often we refer as current, or sometimes it will be driven with some particular velocity. So that makes the flow of charge, which so that will be having different. So that is coming under dynamics. And you have two types of charged bodies. One is positive or negative, and most of the cases we will be taking the spherical shape for the charges for most of the studies, because for with the assumption of the charged bodies are spherical in nature, many theories been evolved, including the Coulomb's law also evolved with the same way. So we can't assume the charged bodies of some random shapes or something. So that is we have to keep in mind. Or we can assume point charge. So point charge, once again, it is a spherical in nature. So that is the some of the key things we have to understand the properties of charge. And of course, charge is conserved, which means you can't create or you can't destroy that. And in other words, it is one of the fundamental nature of the universe itself. So, and all the charges are definitely they are all quantized, and we can also have charges in terms of uh, in a particular line form, also in terms of a volumetric consideration, which will be considered as continuous charges. But most of the places we often use discrete charges. So all the discrete charges, whichever we consider, often comes with two ideas. One is spherical or point charges. That is what you have to keep in mind as a fundamental assumptions. In the very first law we are going to study, that is Coulomb's law. Many people simply, you can also find in some of the commercial or sorry, social medias, that Coulomb simply copied the idea of law of gravitation. Actually, that was not true. Even well before Coulomb's law was spelled out in 1785 itself. Uh, Before that, many people have claimed about that. But the original or the so-called the quantitative approach of the description about this interaction of the two charged bodies was originally given by Coulomb. Actually, he was studying various ideas like friction of two bodies, and in particular friction of two metallic coated bodies. When he studied, he came up with the idea that if you pass the current, what will happen? So once you pass the current of a with a large surfaced body, which are separated by some insulating material, they will be charged. So this charged bodies, they generally have different friction behaviors. So that is where he started the idea of studying it. Further, he separately used this torsion balance, which is often referred as Coulomb's torsion balance, and this is still be used in multiple cases to study electromagnetic field around us, and in many places it's still in use. Even the idea of what we call the voltmeter and ammeters are developed based on this concept only. So what he studied is, actually the idea is very simple. So we have to take a spherical shaped a metallic coated one, or simply metal. But if you reduce the thickness of that, the charge density will be much higher. So that actually you will get the high surface area. And so just around that we have, yeah, again the charged body will be available. So we can, since the area of the sphere is known, then obviously we can control the charge means the total charge available inside this, which other words the static charge which is available. And so the this balance actually will rotate in such a way that for the positive and negative charged bodies, and so there will be a silk thread will be there at this place, and that will control the current flow, and by the way it is constructed. So it's a very simple idea. And so this rotation will take us to that. So in case of study of electrons and such a minute systems, we need laser to find the tilt of that, or different sensors nowadays it is present. Even you can also count one single electrons, that is called single electron detectors. Still it is available. And so this is the starting of Coulomb's law. And what he did is, when he varied the charge density, that is between two charged bodies, when he keep on changed, and the force become higher and higher. At the same time, when the distance is increased, it follows the square root principle. So by the way, he has come up with the idea of Coulomb's law, which very much behaves like the law of gravity itself. So where this electric force is defined, that it is nothing but multiplication of the charge of both the bodies and divided by on the r square, that is the distance square, and that is comes with the uh, proportionality constant, often referred as Coulomb's constant. So this is nothing but 1 by 2 pi epsilon naught, and Coulomb measured this value as 9 into 10 power 9. So this is in his time he considered that as a constant one, but for different material space when it was studied, and there comes a new property that is called the relative dielectric constant, and which will change this Coulomb's constant, by the way. So I think this idea has been later found after the studies of the permittivity all the way. That is, I think, after Maxwell only it was developed. During the times, it is around 19. That's, I think, a 20th century beginning itself. They have found this idea of the relative permittivity, all these things, where actually the interatomic distance, all these things, by that time only it was studied. I think the Bohr, I think he has started the idea of uh, permittivity, permeability all the way by introducing the concepts of spin theory. So this is the scalar form. So where there is no direction of the force is defined, but we know the force is directional dependent phenomena. So by the way, we can define by this. So here K and Q divided by R square, and this ER vector is coming. That is nothing but the unit vector, which is defined with respect to the line joining between these two charges. So we know the unit vector. It is nothing but the AR vector. It is nothing but the R vector divided by the magnitude of the R. So when you do that in the denominator, R cube will come. So that is what we have to keep in mind. And this Coulomb, which defines the amount of charge, is later actually it is further quantified by people like Lorentz and Heaviside, and there comes new theories of electromagnetic fields has come, which is often referred as this Heaviside Lorentz expressions, and later Heaviside alone he has written a big book on electromagnetic field theory, which is the same form till date it is being used. So the theory is very simple. These are the three important statements you have to keep in mind. So in order to write the Coulomb's law, and you're supposed to aware of the various units which are used. Uh, that particularly the Gaussian unit, which is very old text. When you refer books like Hate and all the books, actually they generally put different units. So you should be very careful about that. In the Gaussian units, they generally take this Coulomb constant equal to 1. So which tells the relativity, or means the relativistic concepts between the two charged bodies. So, but Lauren Heaviside was not agreeing upon that. So they have come up with this 1 by 4 pi, which is a very common denominator in most of the cases. And later this being universalized in the international units, international standards with this. So this is what actually we are going to use throughout the course. So you have to keep this all in mind. And some of the interesting facts behind the Coulomb's law, of course, all of you know about that. If there are two opposite charges, they will be attract each other. The force will be uh, positive. Sorry, the force will be negative, and that means actually both the charges actually they attract each other. Otherwise, they repel each other if it is positive. So that's just defined by the sign of them. And the very important thing is this, most probably this is applied for like a spherical shaped charged bodies or simply point charge. So for that only this law is valid. And then another important thing is this two charges should not overlap each other. That means the R is should not be equal to 0. Otherwise, it look like the force is infinite, and that is not at all possible. And because between the two charges, another type of charge will means the force will come that we can study later on, which is very important one. So then, yeah, of course, the charge actually is supposed to be stationary with respect to each other. These are the things we have to keep in mind while considering the Coulomb's law. And this Coulomb's law not only applicable to single between two charges alone, we can have between the multiple charges. So if there are multiple charged bodies or multiple uh, charges, often referred as source charges, which are located at a particular point, let's say with respect to the origin somewhere else, and the test charge upon which the force or exerted is available in another particular point. So in order to calculate that, we have to simply find the line joining between them. we can call it as a R1 vector. Then let's say this is R2 vector. Then this is Rn vector. Like that, actually, we have to find this all these line vectors or the projection vectors between these two source and test charges. And by means of putting it into the summation, then we will get the total force acting on a particular. So since they are all vectorially adding each other, so we can't say that it will be going in the same direction of a particular charge. So it obviously tend to change with respect to the distribution of the source charges. And so this is the vectorial form of the Coulomb's law. And here the R vector is defined. So this can be, when you draw this in pictorial manner, you will understand much more clear. So assume that this is the origin of the particular coordinate system. Let's say if we take X, Y, Z axis, it is nothing but 0, 0, 0. And one point charge is located at a particular point. Let's say this is actually like X, Y, Z. And the test charge is located at X dash, Y dash, Z dash. So now we have to calculate the force exerted upon the test charge by the source charge, which are separated by a distance of R. And so how to find out that? So in order to calculate the force acting on this Q by this force, so which often written in this form. So Q2, small q2, capital Q, like this way. If we define in the opposite way, it will be different. So simply you have to change the direction since the R vector is opposite. So how to find out this R vector? So we already know about that, which is nothing but the X dash minus X, comma, Y dash minus Y, comma, Z dash minus Z. So that is the R vector. So this is actually written in the point form. So we can also write in the vectorial form. So we have to add this AX vector plus AY vector plus AZ vector. That's all. We can easily get the R vector. And this R vector, since it is defined in terms of the Cartesian coordinate system, so we maybe if other source charges also defined in the same form, it is well and good. But in case if they are defined in different forms, let's say you are having some cylindrical charged body and another line charge is available here, you want to calculate the force acting upon that. So in that case, you should be a little bit careful about the coordinate system. We will go to little tricky parts in the future. But it is better, or it is always advised to calculate the unit vector. So this unit vector can be calculated by this R vector divided by the magnitude of the R. So when you substitute this here in this AR, then you will get R vector divided by R cube will come. So that is what it is defined here. So the force which can be represented as this K, that is the constant, Coulomb's constant, small q, capital Q divided by R cube into R vector. So by this, the advantage is you need not to calculate the AR vector separately. So directly substitute the R vector here and this unit vector here. Naturally, you will get the magnitude, and by the way, you can easily substitute this. So this is what is done, and you already know about that in the opposite direction between the two charges, the force will be in the opposite direction. And if you have n number of charges, then you have to take them with respect to the vectorial direction. So for this, we have to always calculate the vectors properly. Then in the denominator, you can see that the respective magnitudes of the, respective lengths or the distance is given. And the numerator constant K is coming. This Q is common one. Only this is going to change. So which can be represented as this K into Q and summation of n number of charges with respect to the unit vectors and the corresponding charges. So in the calculation, in any numerical calculation, it is better to keep this till the end. At the end, you can substitute this 4 pi epsilon naught and this q, or at the end, you can first you have to calculate this summation, then you can later work on it. So that will be very easy to work on the Coulomb's law. And once, so the Coulomb's law describes the force acting on a particular charge due to the source charge. Okay, so this is actually happening in multiple cases, like uh, two charged bodies and how they interact actually. So this is actually in order to describe the alternate expressions being developed in the mid 18th century itself. So that is actually during the time of several people like Lawrence and other people. So I think the original one started with Gauss itself. So where the field in density has come. So that later this gives the idea of the electric field. So the when the force is acting on that, so how this charges sense each other? So that is the question. So there's supposed to be a medium between these two charges, which makes the force or the exerting of force upon that. Let's say one ball go and hit another ball and the next ball is moving. That is all happening in a platform. So similar way, here also there should be a platform should be available. So which we are referring as the medium. So the electric field actually indirectly it is acting as a medium of interaction between the charged particles or charged bodies. So that is the idea of field. So the field is you can assume like water. So whenever you put a drop, then you can see that the wave comes out with respect to that. So this wave is happening in the water. Similarly, if you take a completely vacuum where the electric field, we can say it is maximum, let's say, then you put a charge. So immediately in this particular point, the electric field it will come like this, so it will become a minimum. So by the way, if you put another charge, another minima will come like that. Actually you can think of about the field. The same thing happen applicable to gravitational field or the nuclear field all the way. Okay, so their behaviors are different, and there comes the subatomic particles playing the game. So this the electric field can be, or the electric field, which is nothing but the electric field intensity or the field strength due to the particular due to the source charge, can be described by the this expression that the electric field is nothing but force with respect to the test charge. So in other words, it will be often referred as the force per unit charge. So that is what describes the electric field. So this, since we are dividing this with the test charge, so there is no requirement of test charge to calculate the electric field. So field simply it is nothing but the field exerted by a source charge itself. When we keep another charge, then the field tend to bend, and they generally make the linkage between these two charged bodies by this field components, and that makes the sense to the field or the force itself. So the force need another charged body to to make sense. But in case of electric field, there is no field, means nothing required. Simply if you take a positively charged, then you can see that the field will be going outward direction. And simply if you take a negative charge body, then all the fields will be coming towards it. So like that you can easily imagine. So there is no need of second charge is required to define the electric field. But in case of force, that is necessary. So that is where the electric field and force are linked by this test charge. And we can use the very same expression, only you have to avoid using this capital Q. So that is the minor thing. So this is why actually many people first they calculate the electric field, then they will calculate that. So it is, for instance, if there are multiple point charges, we can easily calculate the electric field due to this each charge at this particular point. Later we have to simply multiply with Q to calculate the force. Either way we can do it. Let's take a simple example, and we can think of how this calculations all been done. So we have 2 point charges. One is 1 millicoulomb, another one is -2 millicoulomb. So they are opposite opposite polarized particles or charges, and they are located at different locations. So we can call them maybe like P and then Q. Okay. So respectively, and calculate the electric force. So we have to calculate the electric force acting on this. So here, this is the test charge, which is having a magnitude of about 10 nanocoulomb located at a particular point. So we can call it as this PQR something. And we have to calculate the electric field at the same point or itself. So how to do that? So for this, we have to use this method of means you in the beginning you always are supposed to draw this picture. Otherwise, it is very difficult to triangulate the problem. If otherwise, you have to keep on practice. So it's best advice to draw it. So there are we have to draw. Let's say there are some origin points 0, 0, 0, which is we call that as origin, and some point P is here and point Q is here, and it's better to use some other term. We can use S because we have the Q here. So another position we have S. Then the test charge is available at the point R. Okay, so they are actually having positions. We can call it as Q1 and this is Q2. Then we have to find the line joining between them first. That is our first job. So we have to find this R1 and this R2. Then we can easily calculate all the way. So that is what we're supposed to do. So the best idea to calculate this R1 vector is nothing but we have to calculate this two vectors and we can find the difference. Otherwise, the very direct method is this is the end point, this is the beginning point. So we have to find the difference between them. So first we will calculate the R1 vector, which is nothing but the 3 minus 2 minus 1 minus 0 comma 3 comma 1. So which is nothing but this PR vector, this PR vector. So we can easily calculate this is nothing but 3 comma 2 minus 3. So minus 1 comma minus 1 minus 1. So minus 2 will come. So this is the R1 vector. Similarly, we have to calculate the R2 vector, and how we can calculate this magnitude of R1 vector. Can someone say what is the value of this R1 vector supposed to be? So how we can calculate the value of R vector? Hello? Yeah, Sohan, please.
Yes, sir. Root 14.
Okay, so how you calculated?
3 square plus 1 minus 1 square plus minus 2 square.
Okay, so that is nothing but 9 plus 1 plus 4. So which is nothing but root of 14. So by the way, we can have this in the, this is nothing but this R1 cube will come, and we can simply substitute this R vector here, and we can finally we can add or subtract up, depends on the polarity. So similarly, you can calculate this R2 vector. So you have to calculate this R2 vector. Then you are finding the magnitude of R2 vector. So this is the second step. Then we are actually calculating the force between this P and between this Q1 and Q. So which is nothing but K Q. So this is the constant, and this is the test charge. Now we are having this the point charge. That is the source charge 1. The source charge is 1 milli. So 1 into 10 power minus 3 Coulomb. And then this R vector. This R vector is going to come. So that is nothing but 3 minus 1 minus 2. So which we can write as 3 AX vector minus AY vector minus 2 AC vector and divided by this magnitude R and cube we have to place. So which is nothing but root of 14 whole cube. So this is how we have to calculate that. So same way we have to do it for Q1, Q, the force between this Q1 and Q, and you will get that. And finally, you have to add the vectorial addition. So that is all. So that is what it is given in this example. So this is the first example given by Sadiku. So here you can see that Sadiku could have given very straight away the answer from here to here, but you can see that he has done step-by-step way. So you can also follow the very similar method or the method what you believe that is. For example, it is straight away given in single lines. But what method I followed is like first I calculated the R vector, then substituted here, then second calculate this Q2 vector Q, and then finally add them both. Then you will get the total. Like that, actually, you can work on. The advantage of this particular method is you won't miss out this positive negative terms. But when you do this kind of a detailed method, many people I have understood that many people they are simply putting plus at this particular point and forgot to do so. Then it leads to mistake. So when the mistakes comes in the beginning itself, the answer completely look different from the original answer. So this, if it is wrong, then this also will be wrong. So that is the problem. So you have to be very careful about that. You can see here, this K and Q is not at all worked out in the beginning itself. It is later substituted. And in many cases, we can see that this epsilon naught is nothing but 10 power 9 divided by 36 pi. So this, if you do that, you will get 9 simply in the numerator will come. And this 10 power 9, this 10 power minus 9, which is nano coulomb, directly cancelled each other. So you have to wait for that. So by doing this kind of problem multiple times, you will understand how to play with these, and quickly you can get that. If you do this way or this method, I'm going to give the same mark, but the time what you are going to consume, that is what going to give you the extra marks. Let's say you have 10 questions, then there are about 3 hours is given to you, then you can easily imagine like around some 17 or to 18 minutes will come for each question, each 10 mark. So in that case, if you spend the entire problem for about 15 minutes, then that means you have, sorry, 20 minutes, 21 minutes like that you are taking, and or you are striking out and again you are starting. So that kind of things you should avoid. I'm telling in the beginning itself because you have to practice in that way. So you have calculated the total force, and unit is very, very important. I will give high preference to the unit. So you're supposed to be very clear about this units. And then once you have calculated this force, then you can calculate the electric field strength or the electric intensity by force per the test charge. So the test charge you are going to place in the denominator and calculate that. Then you will get it. So you can define in terms of volt per meter. Volt per meter is the very common one. So this kilo is added because it become 10 power 10 power 3 will come. That is why they have given here as a kilo. So otherwise you can also put 10 power 3 volt per meter, like that also you can define. So you have to follow some uniformity throughout your exam paper or whenever you do this kind of calculations. I believe you have any doubt on this part? Any questions? These are very, very fundamental ones, because always you should remember, like physics is like going, not jumping from here to here. It is like steps you are actually going. So everywhere actually you should be very clear about that. So if you are clear about that, then this next problem, let's say next we are going to do for some different charged bodies. So at that time you will be very clear about that, and some derivations also. This kind of fundamental is going to appear on that. So you should be very keen about that, and you have to use your so-called IQ as well as some part of common sense all the way, based on the course you already studied, and you can ask questions so that then and there we can solve the problems. There are some exercise problems I have given here. Some of them is given with answers. So you are requested to work out the similar numerical problem and check whether you are doing correctly or not. This is not going to give some great change in your knowledge, but your hand will be practiced, and how to define this nanonewton, how it is all coming. Here you can see it is simply given not with kilovolt per meter, simply volt per meter. So how these all things come up with, and this is one exercise problem given in the uh, in that chapter itself. I think that is the fourth chapter of the study group. So I believe all of you have downloaded the book and try to study upon that, or if it is available in your city or by online, you can bring that. So you can very well buy that book. Plenty of applications are available in law in this Coulomb's law. The very first one is the design of the atomic structure itself. So what we are going to assume is, you can see in a x-axis we have positively charged bodies, and let's say they are actually positively charged protons, and these are nothing but multiple atoms. They are actually kept nearby or positively charged, and these two positively charged are having a periodicity of A, which means their intercharge distance is A, and the same A will be available everywhere. Now, what we are actually going to do, we are going to calculate the electric field due to two charges with respect to the first charge. So this first charge, we are going to assume it is available in the origin, and the second charge is going to be available at x equal to A. The third charge will be available at x equal to 2A and 3A, like that it is keep on going. And at least for the first three charge, due to this first three charge, what is the electric field available, means exerted upon this charge, or vice versa case. So by the way, we can calculate the electric field uh, between these two regions, particularly with respect to the principle of symmetricity. Like we can calculate till a by 2 what will happen. Then next a by 2, very similar behavior is going to happen. So what you will ultimately get is the electric field is nothing but sum of the force exerted by the other charges. And you will see that since all of them are positively charged, so in the beginning you will get at the center, because of this particular charge, at the center you will get the electric field equal to 0, because it is simply going to, if there are two positively charged particles which are kept at a particular distance, then the electric field, they tend to repel each other. And so if you calculate the electric field at this particular point, it definitely is 0. So that is what makes the electric field equal to 0. Interestingly, since there is no material or nothing else is done, or no other charges are specified, this force will act upon that, and it will form another electric field minima at this particular point. So here electric field is already 0. There are electric field multiple places you can find that the electric field is 0 because of, so if you add n number of charges and depends on the distance, then you will get multiple. So like these electric field minimas will come. And if you take the square of the electric field, immediately you will get the potential energy. So potential energy is going to tell that in order to move a particular point charge or something else at that particular location. For instance, in this particular points, the potential energy is nearly 0. So if the potential energy is 0, means there is no energy required or no need of any work done by any point charges at those particular point charges at that locations. That is the indirect meaning. So if you spray the electrons, if you spray some electrons, then what will happen? These all electrons always will go and sit here in this place only, and they will occupy this, and depends on the energy level, they will be occupying at different levels, and that is what makes the orbits. What you see only in the x direction, when you do this in the three-dimensional direction, this point charge around that a sphere will form. These spheres we are calling as orbits. And with very similar theory, if you introduce other quantum aspects like spin, then other quantization and other uh, the band theory, all the things when you put inside that, then you will get the very recent theories of the atomic physics itself will come. So that is the interesting part about this Coulomb's law. And another very common understanding, I think you have studied this particular perspective, that the atomic size is actually we can directly estimate with the simple idea of Coulomb's law itself. If you see that actually this vertical direction when you go in the periodic table, actually the atomic size will keep on increase. At the same time, when you go in the right hand side, then you will see that the even though the number of uh, the atomic number is keep on increasing, then but the size will actually keep on uh, keep on decrease. This is actually because in the vertical side you are actually adding shells, and that increase the number of electrons. By the way, the size of the atom will increase. At the same time, here actually you are adding more number of protons to the atom. By the way, the proton will attract the electron and will make the size smaller and smaller. So this is a simple physical behavior. There are many quantum behaviors might be available. But the simple understanding out of the Coulomb's law itself, we can see that why these atoms are different in sizes. And recently, so many applications are there. I have given only two. The famous, the laser printer, what you see is there will be a drum, which is most probably ionized surface. This is actually called photo perceptor. So there will be a electrolyte will be coated. This electrolyte, they will be charged by means of the light source. So what this will happen, whatever that you are, let's say you are having a document and there are some fonts, and these fonts will be sent as a digital information to this laser, and this laser will point this drum where this is coated with the photoresist, and the photoresist will change the property, and wherever it is changing, it will become neutral. Remaining regions are simply charged. And when you up sorry this wherever this is actually all light sources are placed upon that, they will become positively charged, and the after this light shining upon that with different wavelength, they will become neutral. So this they are ready to attract the they are ready to attract any other opposite charged body. So by where this carbon type black color charged bodies or colored bodies will come into the picture, and they will be sending to this, and that is what printed out of the paper after this ink. So this in case of the big size printers which are used for that, this electrolyte plate itself will be constructed. They will become permanent. For example, those who are preparing notice or newspaper all the way. So these drums will be designed first, and they will be running all the way. But in case of the regular printer, what we call that is actually that actually everywhere this a new electrolyte will be pasted, and they will be drained, and uh, so once again this drum will be used in the different for different documents. This will be completely refreshed. And similarly here you can see that the lithium ion battery, and how this lithium ions are used to charge the electrodes. By the way, it becomes charged, and when it is releasing, when we connect some we call some application, let's say battery or something else, when we put upon, uh, then this load will come. This load makes the current loop complete, and that makes the release of electrons or the lithium ions. And by the way, they carry the negative charges, and this negative charges will travel through the wire and reach the positive electrode. So this is how the cycle takes place. And here also the interaction between the electrodes and the charged bodies, all these things, we can also apply Coulomb's law in partial way. But these here the moving, since the atom means the electrons are moving, we can partially apply that. At least in an instantaneous time, we can apply that. So there are multiple ways we can see the this, Coulomb's law, and this is the very beginning one. So go through that and study again and again. And first of all, read the book Sadiq itself line by line, so that you can easily get the mm, idea. And because this is a kind of fundamental one, and the advanced versions we will see in the few next upcoming classes. If you have any questions, the forum is open. The class is over. Those who want to leave, you can leave.